many carbons it's got. Nothing. All you care about is look at the last chiral carbon, the last one, and see whether the OH is on the right or the left. See, this is the left. See, it makes the letter L. We had someone in big chemistry and society once who couldn't figure that out in the lab, so we showed her that little trick. And makes an L. She was amazed. She went around the rest of the class like, you know what? She's served. Okay. So, what's the answer? Everybody agree it's D? This is a sure 5 points or so for everybody. Can I give you a question? If I give you a question like this. Okay, I will. On everyone's version of the test except for the Lakers fans. All right. Now, number 4. I had to do our preface today. Anyway, because I had to tell you what the lactose. Number 4. Is actually a reaction that you're going to see next semester. Well, in Biochem 2, but it doesn't mean anything because the enzyme type is the same. All right. Can we see the difference between those two molecules? The CO2 is up in one and it's down in the other. Okay, we haven't moved it from one carbon to the other. Okay, we got the same kind of molecule. All we've done is moved. We flipped it. What kind of enzyme does that? No, you guys say it. There you go. It's an epimerase. It isn't a mutase, because a mutase moves something from one carbon to the other. Okay. A mutase moves something from one carbon to the other, like from the number 3 carbon to the number 2 carbon. It isn't an isomerase, because isomerases do things like change things from like ketoses to aldoses. It's obviously not a dehydrogenase or an enolase. Okay? Number 5. I don't know what the hell I was thinking when I wrote number 5.
You weren't here.
There's no such thing. I think it was because I needed to go get one. Just throw out number 5. I was trying to come up with a question where you didn't actually have to do a calculation. And I got caught up in absolute values of things, so just throw it out. But if you went to the trouble, I will point out a couple of things. One, if you went to the trouble calculating delta G's, that was good practice. Okay? And you could also use the Van 't Hoff equation to calculate the delta H if you really wanted to. Because you've got 2 K's and 2 T's. So anytime you got 2 K's and 2 T's, you can calculate the delta H. So you could have calculated the delta H and found out whether it was bigger or less than 0. Whoopee. Aren't you thrilled? Okay. Number 6 illustrates another way that you can do metabolism. It's also a way that they create poisons to kill things. Like one of the versions of rat poison puts a fluorine on one of the intermediates in for the TCA cycle. Fluoroacetate uses rat poison. Or people poison. But for people that take extra copies. Okay. All right. Now, so what the idea is, you notice that there's a fluorine put in different positions. The fluorine's replacing a hydrogen. The concept is if that hydrogen that we're replacing with the fluorine is not involved in doing a reaction, then you don't screw up glycolysis. Like, for example, in this first one. Okay? In the first one, we'll go over here and use this guy here. All right? In answer A, we put the fluorines there. Okay? Those fluorines are, we don't even touch, we go nowhere near touching that carbon, those two hydrogens, right? Not there, they're not touched there, they're not touched there, they're not touched here, they're still here. See, they're never going anywhere. They're never being taken off. Basically, you're looking for hydrogens that you're going to chop off at some point. So they don't go anywhere. So that's not going to, so those hydrogens or that fluorine's not going to shut down the system. Putting a fluorine there will have no effect. It will have a minimal effect, in case anyone says something about isotone effects. Okay. It'll have a minimal effect. All right? So that's why that one doesn't work. Now, let's look at answer B. Let's look at answer B. We'll put these back in each. And we put the fluorine here, in place of that hydrogen. All right? The fluorine starts off there. And then we first do the first series of reactions. We're playing around over here, right? We go from the glucose to the fructose. So we don't touch that spot. So far, so good, right? Here. Still going okay. Nope, sorry, wrong, picked the wrong hydrogen. Okay. This hydrogen here, okay, which is on the number 4 carbon, ends up there. Okay? This is the carbon that turns into the carbonyl in glyceraldehyde, right? This pair of electrons went to there. Okay? This pair of electrons went there, and you form glyceraldehyde, right? So when I get to here, when I get to there, okay, I've got to take this hydrogen off. I've got to take this hydrogen off. Right? This is what the dehydrogenase is going to do. It's going to attack this carbon, and then the NAD is going to come in and go, God, baby, you ain't no hydrogen. Gross! And it's going to leave. So we're not going to be able to do this step because that hydrogen had to come off. Which is why the answer is B. Oh, still work. Okay, A still works. Sorry. I should read my own question. Okay. All right, you see why A works? Okay, you see why B doesn't work? You see why B doesn't work? Anna doesn't, you don't see why B doesn't work. Look, all right, this one, these two hydrogens, right? These hydrogens here, put my glasses out of my mouth, are never touched anywhere in the whole process of glycolysis. They're never touched, so I can go all the way through. Okay? On the other hand, this hydrogen here is touched. It matters. Okay? So because it matters, I can't get, because I have to take it off here. If I have to take the hydrogen off, then replacing it with a fluorine is going to screw things up. Okay? If you look at the next one, at some point you're going to take, if you look at the next one, at some point you may have to take that hydrogen off. But when you go to form the enol, the one in C matters. When you form the enol, with the phosphoenol pyruvate, that one matters. So you're dead. If you look at the next one, it gets screwed. If you look at the one in D, it gets screwed up when you're doing the second step. When you try to form the fructose, you can't do that one. D gets messed up by the first isomerase, or messes up the first isomerase. This guy turns into a carbonyl, which means that hydrogen has to leave, right? When you go from glucose to fructose, this turns into a carbonyl, which means this hydrogen has to go bye-bye. So that one gets screwed up by the isomerase. Okay?